Moving on to a new topic today. What we've talked about so far was how to deal with means. Well, now we're going to talk about how to compare two means. So we can use t-distributions on two samples that aren't matched pairs. So that's what we're going to talk about today. How to run a comparison of two samples or look for differences, probability they'd be different, provided they're not matched pairs. So our null hypothesis is that the two samples come from populations with an equal means. The parameter of interest is the difference between the two means. So let's go ahead and try this. First thing is we have to have some information about each set of samples. We need our mean, the sample size from population 1, and our standard deviation calculated from that sample for population 1. We also need it for our second sample. So the mean, or mean x bar, just so we're absolutely clear what we're talking about here. Let's bring that back up. Our mean for sample 2, our standard deviation for sample 2, the size of sample 2, about population 2. Then we also need our parameters. It's the unknown mean for population 1 and the unknown mean for population 2. Those are what we're interested in talking about today. When we do this, we also have to have our standard error. Before, we're talking about our standard error for the difference of the means is going to be equal to the square root of the sum of the variances divided by their respective sample size. It's a little bit tricky, but it's actually not that different than what we've used before. Now remember, variances always add, standard deviations don't, so we have to use that square root. We're going to get an estimate, okay? It's an approximation. Now using this information, we also can find our confidence intervals. We're looking for the difference, so it's going to be the difference is our estimate plus or minus our margin of error. But don't forget, we're going to need to know degrees of freedom. We're going to need to know it a lot of times when we do this. And then we still have our standard error, hasn't changed. The calculation for the degrees of freedom is kind of crazy, so we're going to let the calculator do it for us. We're going to use the Texas Instruments to do it for us. Of course, we can't do the confidence interval or that until we checked our assumption and conditions. But now we have two samples. We need to check them for both of them. First off, I need independence. I've got to have randomizations. I've got to have random samples. Second, I've got to have sampled less than 10% of the population. 2, I need a nearly normal population assumption. In order to do that, I'm going to plot my probabilities. I'm going to look at my histogram. I'm going to look at my data for both groups and see it's a unimodal, symmetric. I'm going to make that normal probability plot to see that I have it. Lastly, I need my groups to be independent of each other. The two groups we're comparing have to be independent. If I'm comparing husbands to wives, they're not independent of each other. I'm looking at a pre versus post test. Those are not independent of each other. I can't use these particular methods today to compare matched pairs. So to calculate the null hypothesis, well, we're going to keep it simple. Our null is that there's no difference, but we're going to need to find our t statistic because TCDF doesn't let me put in actual values. I have put in the t statistic, which is just like the z-score except for our t. So it's just like before. It's going to be my difference minus my delta null. My delta null is the difference in the null hypothesis. And if you look up here, that's usually going to be 0. So it's going to subtract 0 from that difference. And then divide by our standard error. None of this has changed. It's very similar to how we've dealt with two proportions. It's just our t is the difference minus 0 divided by our standard error. Now using this information, let's go ahead and try one. I have a resting pulse rate for a random sample of 26 smokers. It had a mean of 80 beats per minute, standard deviation of 5 beats per minute. Among 32 randomly chosen non-smokers, the mean and standard deviation were 74 and 6 beats per minute. Both sets of data were roughly symmetric and had no outliers. Is there evidence of a difference in mean pulse rate between smokers and non-smokers? If so, how big? Now to do this, there's a few things I gotta do first. First of all, need to define my parameter. Mu-S, the true mean resting pulse rate for smokers. And if that's one of them, the second one should be pretty clear. It's the true mean resting pulse rate for non-smokers. So I've defined my parameters. Second step, my hypothesis. We said before, a null hypothesis is that there's no difference. Or, in words, there's no difference between the smokers and the non-smokers' mean resting pulse rate. My alternative, we said, is there proof of a difference? That's just, is there a difference? That's it. Mu-S minus mu-NS is not 0. or there is a difference between the smokers and non-smokers' mean resting pulse rate. So if there is no difference between the smokers and non-smokers' mean resting pulse rate, we're going to check for that for alternative hypothesis. That's what we want to prove. So our model, we do have independent random samples. Each is less than 10% of the population, and we were told the data appeared to be approximately normal by saying it was unimodal and roughly symmetrical. So we can proceed with a two-sample t-test. To do that, we need our mechanics. When we set our sample size for our smokers, we had 26. We had a mean resting pulse rate of 80, and the standard deviation for the smokers was 5. For our non-smokers, we had 32 inside of our sample size. We had a mean resting pulse rate of 74, and our standard deviation was 6 for our non-smokers. Well, using this information, we can find our t statistic. But, got ahead of myself, we're going to use that normal model. Finding our t statistic, 80 minus 74, minus our null hypothesis being that there's no difference. Dividing by our standard error, we get a t statistic of 4.15. That means we're looking for our mean of 0. We're looking for the probability of getting that difference of 6. And just say it's just different from 0 means we're going to do a two-tailed test. That's our t statistic is 4.15. But to find our degrees of freedom, we have to use a calculator. Using the calculator, we're going to find that it's 55.95. And we round that up to 56. So we're going to use the t-table for 56 degrees of freedom in order to do this. Now in the calculator, the test that we did, I went to stat test, the two-sample t-test. I input the statistics, and there's a typo. This should actually say 80, but that doesn't change our degrees of freedom. Otherwise, my standard deviation and sample size is correct. So it told me overall, when I was all done, 55.95 for my degrees of freedom. That rounded up to 56. But using that information, I can run the test and get my p-value. So my p-value, it's going to be a two-tailed test, so it's 2 times the probability the difference would be greater than 6. That means 2 times the probability on a T56 table, 56 degree of freedom, of being greater than 4.15. And that works out to be 0.0001. This is a pretty low p-value. So as we've said before, because my p-value is so low, I get to reject my null hypothesis. Doing that, went too far. Doing that, my observed difference is unlikely to just be sampling error. It's strong evidence that there is an actual difference between the resting pulse rate of our smokers to our non-smokers. Now, since I know that, I want to know how big of a difference it is. I've rejected that hypothesis. I need to get my confidence interval. So I'm going to take the difference in the resting pulse rate, find my critical value for a 95% confidence interval, and then use my standard error. Now, those values we've used before. It's 80 minus 74. The critical value I had to find invert t to find, and then the standard error, which we've used before. Doing this, I get a confidence interval of 3.12 to 8.88. And here's what that means. What I was doing was the difference in pulse rates. So the difference is 3.12 to 8.9, and specifically, since it's positive, that had to come from the smokers. That's where we're going to get that positive value from, because my non-smokers be negative. So this tells me I'm 95% confident that my smokers have a mean resting heart rate 3.1 to 8.9 beats per minute higher than non-smokers. And that's exactly what we found. Now again, because we're not pooling data, we do not pool here. We're not using the pooled data. We're still using individual because we're doing means. Like we said, 95% confident the average pulse rate for smokers between 3.1 to 8.9 beats per minute higher than for non-smokers. So let's go ahead and try this for a second question. Here's our saturated fat content in grams for several pizzas sold by 2 national chains. Now be sure to check the conditions when we plot both sets of data. Okay, so we have to see how they normally distribute this. We're going to plot both sets of data. So we have brand D and we have brand PJ. So go ahead, pause the video now, load this information into your calculator. We want to get these inside of, let's just do L1 and L2. Okay, you should be paused. Everything loaded in? All right, so I said fill her up, get it all loaded in there, L1 and L2, and let's go ahead and see what we get. First thing, we need to find our solution. We want to know if the two pizza chains have a significantly different mean saturated fat content. We want to define our parameter. That's what we're looking for. Well, it looks like we're looking for the fat content, so mu D, the average fat content for brand D. Mu PJ, the average fat content for brand PJ. I also want to check my hypotheses. Our null hypothesis, it's the nothing hypothesis, or that there is no difference in the fat content between the two. Null hypothesis, there's no difference in mean saturated fat content. My alternative hypothesis, there is a difference. So all we're saying is that there is a difference. Let's go ahead and try this. So I've done my parameter, my hypotheses. My next stage, I should be doing my model, checking my conditions. Independent groups. Well, two samples, they appear to be independent of each other. They come from separate brands. My randomization. It wasn't mentioned. Nothing was mentioned about how these pizzas were picked randomly or anything like that. But I'm going to have to assume then that they were representative of the pizzas sold by those pizza chains. 10% condition? Yeah, 10 times my sample. My largest sample is only 20 pizzas. 10 times 20 is 200. Obviously, both pizza chains sell far more than 200 pizzas. Nearly normal condition. If you plot your data using the normal probability plot, you end up with what look to be fairly straight lines. They're fairly linear. So I'd say they're nearly normal. As a histogram, you could spend a lot of time trying to get that histogram to come out looking unimodal or symmetric. It's a lot easier to do the normal probability plot. Now, and lastly, it doesn't look like I have any outliers in there either. That's the other thing we're looking for. Do we have any outliers? So once I've done that, my condition met, I can do a 2-sample t-test, and I had 32.757 degrees of freedom from the approximation formula. Now, again, I loaded it in the calculator. I ran this 2-sample t-test, and I found my 32.757 degrees of freedom, so I'd round it up to 33. The other thing you could do is just take the total n, subtract 2 from it, and you'll get pretty close. Now, if you just can't sleep at night without knowing the approximation formula, here it is. And it's pretty ugly. And you put in all the numbers, that's what you get. I like using the calculator. I highly recommend. And we have the calculator for a reason. It's a powerful tool. Let's use it. Okay. The other thing is total n minus 2, something else to think of. Okay. So let's do our mechanics. Sample size for our nationwide chain D, we had 20 pizzas. The mean saturated fat was 11.25. My standard deviation for brand D, 3.193. My national chain for PJ, I had 15 pizzas checked there with a mean saturated fat content of 6.53. My PJ brand was 2.588 for my standard deviation of my sample. My t-score I'm looking for is 0.4823. The difference was 4.72. So on my calculator here, I'm looking for a two-tailed test because I just want to say is it different? And I'm going to check my TCDF. But to get that, 2 times of greater than 4.72 or 2 times exceeding 4.823, and that's how we're going to get our two-tailed test by doing 2 times that. Then we're going to get a p-value of 0.00003. This is a very low p-value. I reject the null hypothesis. There is strong evidence to suggest the pizza brands do have a different mean saturated fat content. Brand D appears to have more saturated fat than brand PJ. So follow up. We met our conditions. We made our conclusion. We rejected the null hypothesis. We should be creating that 2-sample t interval for the difference in the means. And we'll go ahead and stick to a 95% confidence level on this. Specifically, we take our difference, find our critical value, multiply times our standard error, and we're going to find that to be 2.73 to 6.71. So I can say with 95% confidence that the average saturated fat content for brand D is between 2.73 to 6.71 grams higher than the average saturated fat content for brand PJ. That's it. We've done our conclusion. We gave our confidence interval. That's as far as we got to go. So what can go wrong with these? Well, a couple things you got to watch out for. One, watch out for paired data. The independent group assumption needs that special attention. Double check, look at it. Is there a way that this data is actually paired data? If it's paired data, you know you can't use this test. If they're not independent, don't use the two-sample method. Look at the plots. Make sure you check for outliers. Check for those non-normal distributions when you're making those box plots. We can use box plots to check for them also. If you find them, you need to stop. And in fact, this was a classwork. I'm going to stay on the screen for just a second, and then we're going to go back and we're actually going to do a box plot. We'll actually pull down a box plot of our of our brand B and brand PJ data. Okay? So if you need to pause it for a second, copy these down. All right? So let's go back and look at that data. Okay, so here's our data. We're going to go ahead and we're going to load this back in your calculator. You should still have it there. And let's look at those box plots and see if we saw any outliers in those. Okay, so if you still need to, pause the video, get this data reloaded because I'm going to switch over to the calculator for it. All right, so we're back. You must have it loaded already. So let's go ahead. We've got my data loaded in the calculator. So I'm going to out my stat screen there. And we want to know, did it look like we have anything outliers in our box plot? So I'm going to hit my second stat plot, or y equals. Go to my stat plot here, turn it on, and I want it to give me my outliers. So I want this plot. I want the box plot with outliers marked. Ask me for my X list and my Y list. Well, I don't really have one though. Oh, I'm starting with the wrong one. That's what's going on here. I'm like, why do I have both? Here we go. So I hit enter to select that one. There we go. My X list is my L1s. I don't have a Y list. I was wondering why I still had a scatter plot frequency set up. So now I want to see this. So I hit zoom, and it gave me my little error. So I hit second quit. Zoom, 9 for stat plot, and there we have it. We have no outliers being shown. So let's go back in there and try our other data. That was L1. Let's plot out our L2. Now we'll look at that one. Zoom, and again, we get the error. We get it sometimes. Zoom, 9. I have no outliers apparent on this box plot either. So that's a quick way to see it. The other way I said we can see it, if we look at that normal probability plot, so let's go ahead and change that to a normal probability plot. All right, so now we're simply looking at L2 as a normal probability. Zoom 9. It looks pretty linear, and none of those points appear to be off by themselves somewhere. Nothing is that far away from what I would have called probably the line of best fit going through there. So I don't appear to have any outliers, but the box and whisker plots are how I could have seen that if I had any doubt. So with that information, I hope that helped you out. I look forward to seeing you soon. Let's go ahead and try and finish up that classwork, and we'll go ahead and pull up that screen again one last time so we end right there on the work that we're expecting to get done so we can go ahead and move forward. I look forward to seeing you soon.